Good evening, all. Welcome to live session 3 of Fundamentals of Convective Heat Transfer course. Myself, Durga Prasad. So, I am a PMRF scholar from Department of Mechanical Engineering, IIT Madras. And this particular session on my research area lies in the application of CFD for understanding of thermal and fluid dynamics of flows inside building and glazing system. And these sessions are supposed to be helping you to solve your assignments. And the sessions will be happening for next 8 or 9 weeks. And they'll happen from 5 to 7 p.m. every Saturday, and the link will be circulated to all the enrolled students on the registered email ID. All these sessions are recorded and will be uploaded on YouTube. You can access them on this link. And the material that I will be discussing, like the handwritten notes or the slides, will also be shared with you on the Google Drive folder. And these things you can access from your course website itself. If you have any queries regarding the course or exam or anything, you can raise them on the discussion forum. If you have any queries regarding the sessions that I am conducting, you can write to me on me2d2400@smail.itm.ac.in. The Q&A folder can be found on the course portal here, and the session recordings as well as the material discussed during problem solving session can be accessed by clicking on the link here. Okay, let's get started with this week. Let's just start with a quick recap of what we were doing before and how that connects with this week of lectures. So last week we used the scaling arguments. So we started with a problem where we have a flat plate, and let's say we have a uniform stream of fluid that is coming in with some free stream velocity and free stream temperature. Then we discussed that we have a boundary layer that is developing. Then we also saw that there are two different kinds of boundary layers, one for the velocity and other for the temperature. One depending on the Prandtl number, you'll have delta greater than or less than delta T. So which one will be higher one? So let's say this is delta, the velocity boundary layer thickness, and this is delta T. So what would happen? I'm saying delta is greater than delta T. So is Prandtl number greater than or less than 1? No, if you recollect, delta by delta t will be proportional to nu by alpha to the power half. So it will be proportional to Prandtl to the power half. And in this particular case, delta is greater than delta t. So this means Prandtl number should be greater than 1. And we use the different scaling arguments that the velocity, the scale for x direction is the length of the plate, whereas by y direction is the boundary layer thickness. And from that, we arrived at the following set of equations. One, the incompressible flow, which gives us the continuity equation as del u del x plus del v del y equal to 0. And we also have momentum equation only along the x direction, because along the y direction the particular term is negligible. So you have u del x plus v del u del y is given by nu times del square u del y square. And this particular one, we are neglecting the pressure gradient essentially because this is a flat plate. So the change in velocity along the streamwise direction is negligible. So we have from the Euler equation, like the Bernoulli equation, that p plus half rho u infinity square should be constant. So from this we can write dp dx to be minus rho du infinity dx times u infinity. And for a flat plate, u infinity is not changing along the x direction. And then this particular term will become 0. So dp dx becomes 0. So the pressure gradient term from the momentum equation becomes 0. Similarly, we also have the energy equation, which gives u times del t del x plus v times del t del y is alpha times del square t del y square. And from this, these are the governing equations for the boundary layer for thermal as well as the velocity boundary layers. And then we also have our boundary conditions, which says that at walls, we need to have no slip, that is u at y equal to 0 should be 0. And the fluid is not actually going across this boundary layer into or out of the boundary layer. So v also should be 0 at the wall. Now for the v direction, it's only one coordinate. For of course for u1 we have second order derivative, so we need at least two boundary conditions. So one of them is at the wall, and then the other one we will use at the free stream, where we will say as y tends to infinite, this should be equal to infinite, or we can also write this as del u del y evaluated at y tends to infinity is going to 0. Like we are saying that at the free stream there is no shear stress, or in other words, the velocity is tending to free stream velocity. So this is the one that we'll be using. Similarly, for temperature, we have T at y equal to 0 is equals to wall temperature, and T at y tends to infinite is the free stream temperature. So with these set of boundary conditions and initial condition, and the governing equations, we will be able to solve for the boundary layer, both the velocity and the thermal boundary layer. But we didn't actually discuss in the last week how to solve them. So this week of lecture videos discusses how to solve this set of equations by using something called a similarity transformation. The main idea here is the observation that if you were to plot velocity profiles and temperature profiles at different streamwise locations. So this is my flat plate. If I measure velocity at, let's say this is my x1, the profile looks something like this. At the wall it will be 0, and as I go far away from the wall it becomes equal to free stream velocity. Now if I measure the same velocity profile at a different distance x2, the profile looks something like this. So based on these observations, people were able to understand that if I can come up with some kind of a transformation that will merge all these profiles into a single profile, and that is what that is the kind of non-dimensions we have done even long before, where we define u by u infinity to be equals to some function of only one variable. So u is itself a function of x comma y, but when I normalize it with respect to the free stream velocity, then I would be getting it only a function of eta, where eta is called the similarity variable, and it is defined as y times square root of u infinity by nu x. And with this definition, we can substitute, use the continuity equation, like we know the u value here, we can use the continuity equation to get the velocity v, and then we can substitute u comma v into this equation. Similarly, for temperature also, we can use some kind of non-dimensionalization, which says that I will define theta as a non-dimensional variable, t minus tw by t infinity minus tw. So why I'm choosing this particular way is because this way I can make sure that at the wall this will be 0, and at free stream this will be t infinite. So this particular quantity will become 1. That will be very similar to what u by infinity is look like. So this would be my another function. So with these kind of non-dimensionalization, once these are substituted into our governing equations, we get two kinds of equations. One is the Blasius, which is f triple prime. So I'll write this directly. The detailed derivation is there in the lecture videos, which I'm not going to repeat again. Is f prime of eta, where eta is given by this. So we have f times f double prime equal to 0. And then we have similarly for the heat transfer, for again uniform wall temperature, we have the Powerhausen equation, which goes as theta double prime plus Prandtl number by 2 f times theta prime equal to 0. These are the governing equations. So instead of these three equations, now we have two equations. And in the original three equations, we have x comma y as our independent variables. But in this new equation, we have only one parameter, that is eta as our independent variable. And again, these two are kind of decoupled. So once we move to natural convection is where the coupling happens. But here these are decoupled. So first we can solve the Blasius equation, use that f value, substitute in this for a given Prandtl number, we can solve the Powerhausen equation. How to solve that is something we will discuss little later. But for now, these are my differential equations. Now we also need to see the boundary conditions. The boundary conditions are u at y equal to 0 should be 0, which will translate to f prime of 0 is 0. Similarly, v has to be 0, that will translate to f of 0 equal to 0. And then we need u to be equal to u infinite at y tends to infinity, and that will translate to f prime of infinite equals to 1. Similar conditions also for theta. At the wall, theta should be equal to 0. So theta of 0 is 0. And at free stream, that is theta of infinite equals to 1. So this set of equations along with this boundary conditions is what can be solved, and we get the solution. Once we get the solution, what we will be looking at is the non-dimensional numbers that we already discussed before. The solution is again discussed in detail in the lecture videos. So I'll just take the equation and then these are the governing equations that we will solve. Once these equations are solved, we'll have the solution. So the quantities that we are interested in is, one is the skin friction coefficient, which is defined as tau W is the wall shear stress by half times rho u infinity square, where this is basically my dynamic pressure, half rho u infinity square, and tau W is given by mu times del u del y at y equals to 0. And as we have already seen, u is given by u infinity times f prime of eta. So from this solution we get u, then we can substitute that back into this du dy. So essentially this will become del u del y will become u infinity at y equal to 0, f double prime of 0 times d eta by dy at y equal to 0. You can substitute this. Once we get du dy, we can substitute this into tau w, and once we get tau w, we can substitute that back into this equation. And once you do all of this, you'll have to know this particular value, and then this will boil down to this, which is something that we already kind of know, that the skin friction coefficient is related with Reynolds number in this particular fashion. This we already got in the last week when we did the scaling analysis. The only difference now is we need, once we know the f double prime 0 value, then we will be able to calculate the exact equation for this. And as it turns out, this becomes equals to 0.664 by Rex to the power half. This is the local skin friction coefficient. And then we also need to know the overall skin friction coefficient, which is the CFL ball, which is like the average one, which is integrated across the overall length of the particular plate. And that comes out to be twice that of this value. You just integrate it and you can get this. So I'm not deriving this again. Now, similarly, this is for, similarly, we can also derive another one for the Nusselt number, which is given by Hx by kappa, or you can get this as Hx is minus k times del t del y at y equals to 0 divided by delta t into x by k at y equal to 0, and this will become, as you see that we define theta as t minus tw by t infinity minus tw. So from this I can calculate del t del y as tw minus t infinity into minus theta prime of 0. So this I can substitute it back, which gives me okay, or I can just directly write for hx first, then it will be clear, or let it be this. And theta prime of 0 is again something that we do not know beforehand, which we'll get from the solution. You can substitute that back and then get an expression for Nusselt number. I think I did some mistake somewhere. Let me just check again. So Nusselt number is given by Hx by k. K is the thermal conductivity. H is given by the local heat transfer coefficient divided by the local this divided by delta T, where Q double prime is minus k delta del y at y equal to 0. Yeah. So from this, the expression for Nusselt number is given by 0.332. Again, I'm directly writing the Prandtl number dependence here, but this is not straightforward because, as I said, this equation has Prandtl number as a parameter in it. So you'll have to fix one Prandtl number, solve, get an equation for nux. Put a different Prandtl number, again solve, again get the Nusselt number equation, and you have to do that for multiple Prandtl numbers, and then you will have to fit a curve. Then you will get this expression. It is not that straightforward as the skin friction coefficient. Once this is done, then comes the main another one where we have used something called Colburn analogy. The idea here is to introduce another non-dimensional number called Stanton number, which is basically gives you a relation between the local convective heat transfer coefficient and the amount of heat transfer that can be happen because of sensible heat transfer. So this thing is the Stanton number, or this will also come as Nusselt number by Reynolds number times Prandtl number. And what this analogy, Colburn analogy tells is you can use the local Stanton number times the particular fluid property dependence, and this will be equal to the skin friction coefficient by two, half of the skin friction coefficient. So what this helps you is the Stanton number relates the Nusselt number. So if you know the skin friction coefficient, or if you know the drag force or something, using that value, you can use this particular equation. Sorry, you can use this particular equation, and from there you can back calculate the Nusselt number without actually knowing the actual correlation for Nusselt number. So that is the advantage of using this Kalpan analogy. So this is also discussed in the lecture videos. Followed by this is a case where you have Falkner-Scan solution, which is an extension of the Blasius one, where instead of having a flat surface, we will have a wedge. So this is a Falkner-Scan problem. You have a wedge, so if flow is incident like this, then it gets separated on, like, gets developed here, and here boundary layers get developed. And what are the governing equations for those boundary layers and how to solve them is what the Falkner-Scan solution is about. Followed by this is another important concept of displacement and momentum thicknesses, which is something we will discuss in detail in next week also. So I'm kind of skipping that part here. Yeah, up until this, are there any questions? Yeah. Okay. We will discuss about displacement and momentum thickness next week also when we discuss some problems on using them. So for now, I'm skipping that part. So this is a brief recap of what happened in this week lecture videos. We will actually solve some problems to understand how these correlations are actually used to calculate, let's say, net heat transfer or to calculate the drag force, etc. Let's start with one simple problem. So consider a laminar boundary layer formed by the flow of 10 Celsius water over a 10 Celsius flat wall. Derive expression for the total shear force experienced by the wall and the mechanical power spent dragging the wall through the fluid. So the first point you have to observe here is both the water as well as the wall are at the same temperature. So there would not be any thermal boundary layer, only velocity boundary layer will form. So this question asks you to derive expression for total shear force. So we know total shear force is related with the shear stress by the wall shear stress times the total area that is getting exposed. In this particular case, the area will be the length of 2 times the length of the plate, or it's just a tau w times whatever is the length of the plate times the width of the plate in the third dimension. So your plate is like this. This would be the length, and this I'm assuming to be 1 unit. This is the width, and flow is happening like this. So for that particular case, the total shear force will be the shear stress that is acting on the surface times the length times the width, which is 1 unit. So this is this, and tau w is given by, we already know, the skin friction coefficient times the dynamic pressure times length, where the skin friction coefficient is given by, the average skin friction coefficient is given by 1.328 by Reynolds number to the power half times half rho infinity square L, and this will come out to be 0.664 rho L u infinity square times square root of mu by u infinity m. So this is the shear force. Once I have the shear force, power spent is straightforward. Power spent is basically the force times the velocity, which is given by 3 minus half is 5 by 2. We have L power half, and then we have mu power half. So this is the total mechanical power spent on dragging the wall through the fluid. So this is directly proportional to the density of the fluid, directly proportional to the length of the plate. The longer the plate, the more the friction force that it has, the drag force that it has to encounter, like the more power you have to spend. And as the speed increases, also your force increases. And as viscosity increases, these are all straightforward. As viscosity increases, more frictional losses, hence the mechanical power spent should also be higher. So these are all intuitive. Now let's say you're kind of designing something where your idea or objective is to essentially lower this power spent. Like you have to reduce the power spent on pulling that particular wall through the fluid. So we have multiple ways. One is to use a fluid, like you can change something on the wall because a fluid is kind of fixed. Let's say it's something that is underwater, some underwater thing, a torpedo or something that has to move inside water. So the fluid is kind of fixed. So rho is kind of fixed. L is something is in your design variable. You can change the length of it. V is the velocity with which you move it, which is also kind of something that you can change. But there are always requirements that will fix the U. So the parameters that are of interest are only this. But as I said, the fluid is kind of fixed. So what can we do that will vary the thermophysical properties? Yeah. So the thermophysical properties will depend upon the absolute temperature of the particular fluid. So what we can do instead is we can increase the temperature of this particular surface by heating this or something. That way what would happen is these properties will change. So if you heat a surface, then the fluid near the surface will also get heated and its temperature will increase. And as temperature increases, viscosity will reduce. And if viscosity reduces, the total power spent will also reduce because they are directly proportional to each other. So that way we can reduce the power spent. So that is what we will discuss in the next problem, where we will heat the wall to 90 Celsius. So the power spent is given by the previous cases when the cooler fluid. Now I'm saying we'll also change the heater power. Sorry, when the plate is heated, this will be nu h to the power half. Now the question asks you to find the reduction. Okay, I should say pH. It's not pH. Reduction in the dissipated power as a percentage or something. So you can calculate PC is the one. Now because when you heated it with properties change, so power should reduce divided by the actual power. So quantity like this. This will give you the percentage reduction that is happening. Or you can simply calculate pH by PC, whichever it is. If you calculate one, you can compute the other one. So that is what the question asks you to find. So for this, I need to know the viscosity values. So this is water. So I know for water, viscosity varies with temperature by an expression like this. You have to take in Celsius. So the only problem now is to figure out when what value of temperature I have to use so that I can get the viscosity correctly in this expression. So which temperature would you be using? Now I have two different temperatures. I have the fluid. This is my surface. The fluid is going like this, which is coming at U infinity, and then I have it as 10 degrees Celsius, while the surface itself is at 90 Celsius. That is case 2, or I'll just call it case H. And then there is another scenario where the surface is 10 Celsius and the fluid is also flowing at U infinity and 10 Celsius. This is case C. So for case C, it is straightforward. The temperature that you would be using is 10 Celsius. There is no other temperature. So what would be the temperature I should be using for case H? Yeah, take a minute and try to understand it from the point of view of this this figure. So you can see that there are two different temperatures, and this nu should refer to the viscosity of the fluid, viscosity of the fluid where the flow is actually happening, where the flow is actually affected, and this viscosity is a function of temperature. So what viscosity value should I be using to get an reasonable estimate for the pH value here? Take a minute and then answer. Say if I want to plot the temperature on, so this is my y coordinate and this is my temperature axis. So I'll have 90 Celsius at y equal to 0. So this is my temperature axis. I'll have 90 Celsius at y equal to 0, and it will become 10 Celsius at y equals to, so the profile will be something like this. So this is when y becomes equal to delta T and so on. So because temperature keeps changing across the boundary layer, we'll have to use only one reference value. And that value is going to be the arithmetic mean of the wall temperature and the free stream temperature. This particular quantity is called the film temperature, which in this particular case will be 50 Celsius. So the idea we are trying to show here is if you use either only this or only this, would either be over or underestimating the actual power consumption or essentially the viscosity value. So the reasonable estimated use is to use an arithmetic mean, and with that, and that is the temperature. So across the boundary layer, temperature changes from 10 to 90. So the first order approximation for any profile, whatever profile this is going to be, like if you do a Taylor series expansion of the property values, then so for example, this nu of t, I can do an expansion around the mean temperature. At any other point, it will be plus or minus delta t. So this will be the value at Tm plus evaluated at Tm times delta t and so on. So we are what we are implicitly assuming by doing this kind of approximation is the viscosity value at any temperature above or below the particular value of Tm is going to be the value at the mean temperature, that is the film temperature, plus this is the approximation plus other higher order terms. And we are assuming that the property changes with respect to temperature times this delta T that we are going to have is negligible compared to the actual value here. So you can actually use this particular correlation, evaluate these terms and see how good this particular approximation is for this particular fluid water. You can also do this for air. You can see different and you can observe that okay, under certain scenarios you'll actually observe that doing things like this are not appropriate. We might actually have to consider variable properties across the boundary layer under some scenarios, not always though. Anyways, the idea is once we have this filling temperature, you can substitute that back here and then calculate the values of pH by PC. When I did, I'm getting around 0.65. You can also just check and let me know. So I got nu C to be around and then from this pH by PC is going to be nu H by nu C to the power half. So that you can substitute back at pH by PC. Once I get this, this is straightforward. This is basically 1 minus pH by Pc, so that is around 35% reduction. So we are getting around 35% reduction by actually heating the surface. But that is not at like we are getting some benefit in that, but then yeah, we actually have to heat the surface. So which means we have to spend some energy to heat that. So is this particular strategy really advantageous or not? In order to answer such questions, what we have to do is understand the amount of heat that we are supplying also. Only then it becomes clear whether this particular strategy is effective or not. So what I'm trying to say is I'm getting power savings, which is Pc minus pH. This is happening because I have increased the temperature. But in order to increase the temperature, I will have to heat that particular surface. So I'll have to spend some energy. And under equilibrium conditions, the amount of energy I'm giving to the surface should be equal to the amount that is being absorbed by the fluid. And only in that condition, we can assume that the temperature reached steady state on the surface. And if we are assuming it to be isothermal, so what I'm trying to say is Pc minus pH is the savings I am getting should be greater than or equal to the amount of energy I am spending, which is Q, is H times average heat transfer coefficient times length times TH minus TC, where TC is the freezing temperature, which is like we know TC equals to T infinite, and TH is the 90 Celsius that we have. So this is just right here. TH is 90 Celsius and TC is 10 Celsius. So only when this criteria is satisfied, we can actually come to the conclusion that we have a net energy savings. And now we also need to figure out what these values are. So Pc and pH are something that we already know. Pc is given by 0.664 rho L to the power half to the power 5 by 2 nu C to the power half minus 0.664 nu H to the power half should be greater than or equal to. How do I get the heat transfer coefficient? Yeah, we have two non-dimensional numbers. One is with respect to the skin friction, the other one is with respect to the Nusselt number. That is what we will be using. So the mean Nusselt number is given by H bar L by kappa is the thermal conductivity, which is 0.332 times Reynolds number to the power half times Prandtl number to the power 1 by 3. So from this we can estimate the H times L, which is this one. So that will go as 0.332 times kappa times TH minus TC times U infinity to the power half L to the power half nu H to the power minus half Prandtl to the power half. Is this clear? Now what we are trying to do, the first part of the question asks you to find how fast must the water flow be. So which means I need to determine the U value. So I can just take the, I think L power half gets cancelled. And then we have a U infinity here and a nu H to the power minus half here. So I can take them to RHS. If I just rearrange these terms, so I'll have U infinity square, which is U infinity greater than or equal to square root of, this will be 1 by 2 here. So I'll have Prandtl to the power 1 by 3 by 2 times kappa TH minus TC by this comes here, so half square root of nu C nu H minus square root of 2 times square root of nu H whole square, which is nu H. So the water flow has to be minimum this value. Only if the velocity is greater than this particular value, we will have the net heat transfer that we are adding to the heater less than the savings we will be getting from the reduction in the drag. Did I miss something? Ah, okay, okay. There is a row term here also. So this will come in the denominator. Okay. Yeah. And yeah, you need the values to compute this. So this is for water. How do you look for the values? You'll have to look for the values of all the thermophysical properties should be taken at the film temperature, like I said before. So in this case, the film temperature is 50 Celsius, which we already calculated before, 90 plus 10 by 2. So take the Prandtl number at 50 Celsius. For water, that comes around 3.56. In thermal conductivity also, you take at the same temperature for water. It's around 0.64 watt per meter Kelvin. THTC values are already given. Nu C, nu H are also given before. These are nu C, nu H values. Once you substitute the values, you can get the value of the critical U infinite. So I'm getting this around, it should be greater than or equal to 180 point something, 180.9 meter per second. You can also check this once. And next question asks you to how short must the swept length be so that the boundary layer remains laminar. So for that, we need to know what is the transition criteria. So the transition criteria for a flat plate is the Reynolds number should be less than 5 into 10 power 5. So which brings us U infinity times L by nu H should be less than or equal to 5 into 10 power 5. We know the value of U infinity, we know the value of nu H, we know all we need to do is find the value of L. So only if the length of the wall is less than this particular value, then this particular assumption holds. Because we are actually using the correlations for flat plate that are derived under laminar flow assumptions. So we also need to make sure that the laminar assumption, the criteria for laminar assumption is valid, which is this particular criteria, that Reynolds number should be less than or equal to this. We have also made another assumption regarding that this particular flow is incompressible. So as I said before, in the week one lecture, you also need to verify that the incompressibility actually holds. And for that, you will have to calculate the Mach number and see if it is less than zero point 0.3. If it is less than zero point 0.3, then the error that you are going to get from this is will stay within 10%. If not, then the error will actually increase and you will have to decide whether you have to move to compressible or not. Okay. Are there any questions? Yeah, you can quickly compute this value and let me know. So this is like 0.5 of this, so this is around 2.5 by 180. So we have 0.25, 1 by 4, 72, 1 by 720. So this value is going to come in millimeters or something. So this is very, very small objects that you have. I think this arithmetic you can calculate this. So I'll move on to the next problem. This one is again a straightforward problem where we have a flat plate that is suspended in a room and is subjected to airflow parallel to its surface along the 3-meter long side. So if I have surface like this length is given as 3 meter and flow is happening like this. The velocity is given as 7 meter per second and the air temperature is given as 20 Celsius. If the total drag force is 0.86 Newton, you have to find the average heat transfer coefficient. How do you approach this problem? So as I said, this problem you can actually use Kolban analogy straightforward instead of Reynolds analogy, where we have the Kolban's analogy given by the Stanton number times Prandtl number to the power 2 by 3 is skin friction coefficient by half. And how is the skin friction coefficient related with the drag force? The total drag force is given by the shear stress times the total surface area, which is the area of the plate A. But since this is suspended vertically and we have flow on both the sides, that should be multiplied with the factor of 2, just to account for both the left and right sides of the plate. So that is 2 times tau W times A. And tau W is given by skin friction coefficient times rho U infinity square times this is tau W times 2A. This comes as, so from this I can write CFL by 2 is the drag force divided by 2 rho U infinity square times the area. Now what we are trying to find is we need the heat transfer coefficient. So Stanton number, we need to know the Stanton number relation between Stanton number and this one. So now the next step is finding the Stanton number, which is given by Nusselt number by Reynolds number times Prandtl number. And this will also eventually come down to the average heat transfer coefficient divided by rho Cp times U infinity. As I said, this measures the rate of convective heat transfer, and this is like the residence one, rho Cp times delta T. Instead of delta T, we are having rho Cp U infinity. This is as if a particle is coming, taking certain amount of heat and going away. As the velocity increases, the amount of heat that it can take with it will also increase. So that is this term. This is the total heat transfer coefficient because of the total heat transfer due to convection. So this will give you the Stanton number, and what now we have the relation between this equals CFL by 2, which is equals to FD by 2 times rho U infinity square times A. So from this we can compute H bar as FD times Cp divided by 2A times U infinity. Yeah, and we also have this is Stanton number, so this should be divided by 2 times Prandtl number to the power 2 by 3. So, we have that Prandtl number to the power 2 by 3 here. So all we need to know now is the values that we need here. So drag force is already given as 0.86, and then we need to know Cp. Cp for air at 20 Celsius is 1006 or 7 joule per kg Kelvin. Area is again, since I already considered 2 times area here to calculate total area, area is just on the one side surface, which is 3 cross 2, 6 square meter. And for air, the Prandtl number around 20, at 20 Celsius is around 0.73. U infinity is already given as 7 meter per second. So you have all the values that you need, and you can substitute them in this equation, which will give you the heat transfer coefficient. That comes as around 12. You can actually check once yourself. I'll wait for a minute. So you can also try to calculate this yourself and then see how the flow. So you start from the Kolban analogy, where we need the skin friction coefficient related with the drag force, and then we use the Stanton number definition to calculate the average heat transfer coefficient, which is related with the drag force by the following equation. There any questions? Yeah, I think we can move on to the next problem. Yeah, this is another one where I'd just like to emphasize on because this is not discussed in detail in the lecture videos. For those of you who are interested in actually solving the Places equation, it's like in the lecture videos we have started with the Places equation and we did not actually solve it. So let's see how to solve this. So to those of you who are already familiar with the state space form, you can kind of skip this part and move on to the next section. But for now, I'll just start with what's how to solve an differential equation of higher order. So first we need to know how to solve a differential equation which is of let's say first order. So let's say I have a differential equation of the kind f prime equals to some g with some initial condition that says f of 0 is f naught. How do you solve this kind of equations? Is something that I'm assuming that we already know. This is an initial value problem where you will be given an initial value and you will be told how the rate of change of that value as a function of time. Knowing these two informations, you will integrate forward in time and solve. So I'm not going to discuss how to solve this problem for a first order ODE, which again you can discuss, you can check in any numerical methods course where they will in turn discuss different kinds of methods like Euler explicit, implicit, and then you have Runge-Kutta. Different methods are already there and different solvers are already existing in say open source softwares like Python, or if you use MATLAB or something, solvers are already existing for this kind of first order ODEs which have of this kind initial value problem where an initial value will be provided and you'll be asked to integrate forward in time. So that is something that we are assuming as a prerequisite. Now with if we have a solver that can solve this kind of equation, then how can we extend that solver to solve our particular problem, which is the Places equation. So our the Places equation is a third order ODE. So first we have to reduce it to a first order ODE. So that's where the state space form comes. So we take the original equation and we define new variables like so what we are trying to do is convert from one higher order ODE to n, or let's say one, what we are trying to do is to convert one nth order ODE to system of n first order ODEs. Once we do that, then it is basically a system of simultaneous equations that I will be solving. So essentially it will be a system of n first order ODEs. We already have a solver which can solve first order ODE. All we need to be doing now is this f comma g will are not scalars, but now there will be vectors. And all we'll be doing is just use the same solver and then just extend it as if we are treating each and every field like as a vector problem. But for that, we also need to have two things. One, we need to first convert this ODE, like higher order ODE, into first order ODE. So we'll have an equation of this kind. Second, we also need to have the boundary conditions given in such a way I can write like this so that I can formulate the problem as initial value problem. First, we will see the differential equation, then we'll move on to the boundary conditions. So for the differential equation, we have f triple prime plus half into f double prime equal to 0. So let's define some new variable x1 as f, let's define x2 as f prime and x3 as f double prime. So as I said, this is a third order ODE. So we'll be converting this into three first order ODEs. So the three variables for each first order ODEs are defined as x1, x2 and x3. x1 is equals to f, x2 is equals to f2, f prime, and x3 equal to f triple prime. Now I will write my equation as x1 prime, the first equation, the first ODE will be for x1 prime. That will be equal to the derivative of this, which is f prime. And f prime is equals to x2. So this is my first ODE. The second ODE will be x2 prime, which is equals to f double prime, which is x3. And for the third ODE, which is x3 prime, is sorry, sorry, this is f double prime only. X3 is f double prime, so this will be f triple prime. For this, we will use the differential equation directly. So this is my differential equation that I will be using. So f triple prime is given by minus half f double prime, which will be minus half f is x1, f double prime is x3. So now you can see I have three first order ODEs. So my original third order ODE is now converted into three first order ODEs. So I'll have to treat some vector x as x1, x2, x3, and then just solve this system of ODEs. Provided I can use a solver only if I have my initial conditions. So let's also see what the initial conditions are. X1 of 0 is going to be f of 0, which will give me one condition. X2 of 0 is f prime of 0, which is also equals to 0, which is also given in my original boundary condition. And x3 of 0 is f double prime of 0. But this is an unknown that we do not, this is basically an unknown which we do not know. This is something that relates with our spin friction coefficient, and which is something that we do not know beforehand itself. Instead, we know something else, which is x2 of infinite, which is f prime of infinite, which is 1. So we know this quantity, but we do not know this one. So if we do not know this, we cannot actually pose this problem as an initial value problem and solve it. So that's where the trick comes. So one approach to do that is you assume a value. Assume something like f double prime of 0 equal to some quantity, let's say 1 or something. And then do your time marching, which I am calling as integration, forward marching. Integrate to get f prime of infinity. So you start with assuming f double prime of 0 equals to 1, and then you do this particular, use the solver, get a value of f prime of infinity. And ideally we would want that to be 1, but it will not be equal to 1. Then what we will have to do is, now we'll have to update the initial guess that I have taken and again integrate it. And I have to keep doing this till I'll reach a convergence. And in order to do this upgrade, one way is actually you use some kind of solver like Newton-Raphson or something, some nonlinear solver that can solve the system of equations. But in order to do that, each and every time you would have to do the integration, which is the most time consuming part of the entire steps. So an alternative way to do this is to understand something called invariance. Let's say initially whatever we are solving, let's change our equation as follows. Uh, let's define a new variable psi as eta by p. So basically we are scaling. So because these are kind of similarity equations, scaling should not change much. So if I define psi as a new variable, which is eta by p, where p is some scalar, and then I'll define some function g of psi as b times f of eta, which is basically b times f of psi b. So if I introduce this kind of transformation, what I'm expecting to do is, now let us consider the equation itself. Our original equation is f triple prime plus half f double prime equal to 0. This is always satisfied. So f is the actual solution, and this g is a solution I will get with incorrect guess. So what I'm trying to do is when I took such that is with g double prime of 0 equals to 1. So if I've taken g double prime of 0 equals to 1 and then solve the differential equation, and my differential equation is g triple prime plus half into g double prime equal to 0. If this is my differential equation, you can actually verify that this and this equations are equivalent. This and this equations are equivalent. You can just quickly check that one also. So we have g defined by g of psi is given by b times f of b psi. So you can compute g prime, which will be b square, because the derivative of this will also come. So b will come outside, times f prime of b psi. You can also calculate g double prime, which will be b cube times f double prime b psi. Also compute g triple prime, which is b power 4 times f triple prime of b psi. So if I substitute this equation back here, so I would be getting g triple prime as b power 4 into f triple prime plus half into f double prime, which will be 0. So essentially by doing this transformation, whatever I am saying, you will end up with the same equation. The differential equation is not going to change. However, the boundary conditions, now we also have to look at, like, a particular equation is governing some particular system. It's not just the differential equation, we also need to worry about the boundary conditions that we are going to have. And once we see that, the boundary conditions are, we need the conditions that we have imposed are g of 0 is 0, g prime of 0 is 0, and the condition I imposed is g double prime of 0 equals to 1. And with these boundary conditions, I got g prime of infinite as some constant a. This is what we have. And what we want is f of 0 is 0, f prime of 0 is 0, f double prime of 0 is something that we do not know, but f prime of infinity is 1. So we know that this kind of transformation, whenever we are doing physically, what we are doing here is we are just scaling the eta variable and g accordingly scale. So it's essentially when you vary your eta, all you're doing is you're varying your u infinity. So u infinity will be scaled accordingly by the same factor and nothing will change physically. So if such kind of thing happens, your boundary condition should also hold equivalently. So what I mean by that is if I calculate g double prime of 0 from this equation, so if I use this equation, from this I can calculate g double prime of 0 and relate it with f double prime of 0. So I can compute f double prime of 0 that I need to be using from g double prime of 0 by b cube, and this is equals to 1. This implies f double prime of 0 is g double prime of 0 I have taken as 1, so this will be 1 by b cube. I have f double prime of 0. Now I also need to maintain that f prime of infinity should be 1. So which means I'll use this equation, which has g prime of infinite is b square times f prime of infinite, which is equals to a, the constant I get by integrating it once. Now from this I can calculate b square equals to a, because f prime of infinity is 1. So this implies I can substitute that back into f double prime of 0. So b square is a, so this will be 1 by b cube, so this will be a power minus 3 by 2. So what did we come to? So what we came to is we start with an initial guess g double prime of 0 equal to 1, and then we will calculate, we will do the integration using the solver that we already know that can solve a first order ODE with the time marching method. Then evaluate g prime of infinite. So when we are numerically evaluating it, we do not actually go till infinite, we will stop after 10, 20 or some value beyond which the value of g does not change too much. Then we'll compute that value and call that as a. Now once we have it, all we have to do is take a to the power minus 3 by 2 and use that as our f double prime of 0. and then again do the like that will be the f double prime of 0 that we need. And once we solve this equation, we get everything. So we know the b value, like you do not even have to solve for the actual value. You can actually map these values. We know the transformation between g and f. So if you need to know the actual value of the solution at any value of theta, you have to just use this transformation. And from there, you can compute it again. So you do not have to integrate it again and again. So you'll be using the solver only once, and then you'll have the entire solution available to you. Let's also see how to solve this in, let's say, Python. So to those of you who are already familiar with Python, it's okay. And to those of you who are seeing it for the first time, so the first few lines here are about if you're already familiar with some programming language like say C or C++, where you would be doing some kind of hash include or something where you will include the libraries. So these statements are similar to that. So we have a function called solve IPP, which is the initial value problem in SciPy module. You'll have to download this module. So this particular platform is called Google Colab. It has all the modules, most of the modules that I'm using are already installed in it. So all I have to do is just import them. So the first one is to kind of deal with the arrays. The second line is to import the function that solves the initial value problem. So as I said that we are assuming that you already familiar with numerical methods that can solve initial value problems. And of course, there is another function called solve BVP within the SciPy module that I would leave as an exercise for you to explore, in which you do not have to solve like the one that I'm doing currently, where it kind of like it does this loop automatically. So it implements a solver that will automatically take care of this and it will give you the final solution directly. So I would like you to explore that particular one, which I'm not taking here. So one is the solve IVP, and then this is something that just for plotting which I have not used. Okay, I can remove this. First step is to determine your system of equations. So how you write that is a function. Def is a keyword that defines a function. System is some name that you can give for the function name. And then the argument comes as t comma x. These are the specific arguments it has to follow. T is the independent variable and x is the dependent variable that you are solving in your system of equations. Because x is a vector in our case, I'm just splitting into three different equations, x1, x2 and x3. First equation is dx1 dt is x2. Second is dx2 dt is x3, and third equation is dx3 dt is minus half x1 x3. So that is similar to what I have written here. X1 prime is x2, x2 prime is x3, and x3 prime is minus half x1 x3. That is the same thing I have written here. Once the function definition is done, now we'll have to define the initial conditions and the domain on which I have to do my integration. The initial conditions are for x1, which is f is 0 at 0, and f prime is 0, and f double prime is basically I am making an initial guess of 1. With this, and I have to define the range on which I am doing the integration, which varies from 0 to 10. Once this is done, then we'll have to just solve it. You just call the function solve IVP with your system of differential equations, the domain on which you are integrating, and the initial guess. Once you do this, it solves the system. You can see the solution here. The solution says that the integration it reached convergence, and it returns two things, t and y, where t is your dependent variable. So these are the values of eta in our particular case, and y is a vector which has again multiple vectors. So what this says is along this direction, these are at different values of t, or basically the eta values. And the first row is basically f, second row is f prime, and third row is f double prime. So what we needed is f prime of infinite. So you have to be taking the second row last quantity. So that is 2.086. So that is the value we got, and that is this particular A I am talking about. So once you do the integration, you get a g prime of infinity A. So I can use this A value, substitute that back here, and I'll get f double prime of 0. Once I do that, I got f double prime of 0 to be around. So A we are getting around 2.086, and from this you can calculate f double prime of 0 to be around 0.332. You can also use the solve IV boundary value problem, solve BVP function that I commented here. You can also explore this and see that you are getting the same value. Okay, there any questions? Okay, then we'll move on to the next problem. Again, I think we have done enough of this derivation, so we'll actually take some numerical problem, which is again a straightforward one. So you are given a free stream velocity and temperature, and you are asked to find boundary layer thickness at different values of distances from the leading edge. So in order to solve these kind of problems, you would have to know the relation. So in this particular case, we know that delta as a function of x is given by square root of rex, or you can write this as 5 times square root of mu x by u infinite. As I said before, nu has to be calculated at 300 Kelvin for a year. I just substitute the values. Nu is around 1.85. U infinity is the free stream velocity. X are these different values, 1 mm, 10 mm, 100 mm. You can substitute those and you can get the values of delta. This is a very straightforward exercise. So there is nothing much in this. So you can calculate this. And then the other part of the question says, if a second plate were installed parallel to and at a distance of 4 mm from the first plate. So what the question says is you have two plates like this, and you have two boundary layers that are developing. So after a point, both of this will merge. So you are asked to find the distance, this distance, if the separation between the plates is 4 mm. How do we do this? Yeah, one simple way to go ahead is to basically say calculate the delta value here, calculate the delta value here, and say that 2 delta is equals to 4, and that distance will give you the corresponding length. So what I'm trying to say is you calculate 2 times delta, evaluate it at L, and make it equal to 4 mm, which is basically 10 times square root of mu L by u infinite equals to 4 mm. And once you solve this, you can get the value of L. Like for now, this is how you proceed. Then you also need to make sure another difference here. When we are deriving this equation, this particular equation, when we derive, we assume something, that the free stream velocity is constant as a function of x. However, in this kind of flows, free stream velocity is not constant. The velocity here, as it goes here and here, it gets narrower and narrower, in the sense that you have these gradients here. So the velocity, the fluid actually gets accelerated, which means your pressure gradient is not zero. So this term, the constant that we used here, phi, may not actually be phi. It can actually increase or decrease. What would happen to that? And because of that, the length that you'll be getting might be higher or lower than the actual region where the merging happens. And that all, how that happens and how to apply the corrections, etc., is something that we will discuss a couple of weeks later once we move to internal flows. But for now, the idea is to make you understand that, to visualize, so that you can understand that, okay, when you have two different surfaces, it's not just external flows. Even under internal flows, there are certain conditions where the assumptions that we are considering for a external flow might actually be valid, and you can simply use the boundary layer correlations like the Nusselt number correlation or the skin friction coefficient that we derive for flat plates under certain conditions, only under certain limited conditions. The question now is, under what conditions? How do we get those conditions? These are all the questions that we will discuss a little later. But for now, I think the idea is clear. So now you can visualize this as two boundary layers that are merging. And from this, you can get the value of length where the merging happens. The third part of the question asks you to calculate the surface shear stress, which is a straightforward one. So you know delta x and tau w is given by rho infinity square, and CFL is given by, with this equation, you can calculate the surface shear stress. So I'm getting values like x, let's say the local Reynolds number, delta in the shear stress. So X is say mm, 1 mm, 10 mm, and 100 mm. The Reynolds number uh, increases linearly with this. So if it is 811, the other one will be 81100. The boundary layer thickness I'm getting it's 0.176. So you can see this. If X increases by 100 times, my delta increases by 10 times because delta is proportional to square root of X. And the shear stress values 3.09. This also the same thing. As X increases 100 times, your shear stress reduces by a magnitude of 10 times. And you can see as the length of the plate increases, the net shear stress will also gradually decrease as a function of X. Oh, sorry, I have to use a different equation. So this is a local shear stress. So you should be using the local skin friction coefficient, which is 0.332. Just check these values again. They can be reduced by a factor of 2. You can check those values again. But this is the important relation that you have to be using. Because this is a local shear stress that we are asking, you need to calculate use the local skin friction coefficient to calculate the shear stress values. Yeah. Are there any questions? Okay. I will take another simple problem. A couple of more problems. Okay. This one is a very simple one. So this is to understand where the assumptions are actually valid. So for a flat plate, we need to have the Reynolds number less than 5 into 10 power 5 so that our laminar assumption holds. So in this particular case, you need to find the length where this particular thing happens. So this is the local Reynolds number. So you have this as u infinity times x by nu less than 5 into 10 power 5, and u infinity is given as 8 meter per second. Nu for a year, we can take it as 1.85 to 10 power minus 5. So with these values, you can calculate the x and getting to be less than around 1.16 meter. You can quickly check this. This is straightforward one. Again, uh, there are always assumptions that we'll be considering when we are solving these kinds of problems. It is important to know the assumptions, and you also need to know how to verify those assumptions. So for example, the assumptions like incompressibility, you calculate the Mach number and verify if it is less than zero point 0.3. And the assumption about the laminar layer, you will use this particular transition criterion that I have given here, that the local Reynolds number should be less than 5 to 10 power 5. Again, this particular transition criterion is a geometry configuration dependent one. This is valid only for a flat pipe. Later, when we move to internal flows, we'll have a different criteria. So you'll have to know which criteria to use. And only when you know how to verify your assumptions, you can actually comment on whether the results going to get from using these assumptions are valid or not. So for example, you have a particular plate, you calculated the heat transfer using the correlation that we derived for the specific case where you have Nusselt number given by 0.332 times Reynolds number to the power Prandtl power 1 by 3. If you use that correlation, you got certain value of heat transfer, but the actual heat transfer is not matching with that. Then there could be multiple reasons for that. So in order to figure out what are the actual reasons that caused it, you will have to verify each of these assumptions. You will check whether the Reynolds number is less than 5 into 10 power 5. If that is true, okay, then you will check the velocity, calculate Mach number, see if it is less than 0.3. If that is also true, then comes other things like the property variations with respect to temperature. I told you before, you would have evaluated them at film temperature. or you might have done something wrong somewhere else, or if you do not have thermal boundary layer at all. Or you can also have the other assumptions might be wrong, like in flat plate assumption in the boundary layer equation that we derived, we assume that the pressure variation across the horizontal or the streamwise direction is negligible. Maybe in your case that is not true. Maybe your u infinity is not constant. So you will have to go step by step to understand which assumptions were wrong, so that that could actually explain why you are getting deviation from your theoretical prediction versus the actual real scenario that you are considering in question. So knowing the assumptions alone is not sufficient. You also need to know how you can verify your assumptions. So keep that in mind. That's it. I have one more last problem I have. This is just kind of an extension so that you kind of can get familiar with how to do similarity transformation yourself. So the one that is discussed in the lecture videos is where we neglected this particular term, which is the viscous dissipation term, and we discussed this extensively last week also, where we identified that for under normal conditions, when you have very low Mach number flows and for air kind of gases, this particular term is neglected. Of course, for fluids which have higher viscosity like oils, engine oil kind of stuff, this term can become significant, which is not considered usually in our case. But just in a case, just to make you familiar with the similarity transformation, you can try to extend the similarity analysis and derive the corresponding equation, just like the Paul-Hausen solution. Derive the equation for this similarity equation for this particular case. So what would be my steps? First step is to non-dimensionalize this equation. So I'll have to define a quantity, which is again another difference between this and the one that is discussed in the Paul-Hausen solution is here we have an adiabatic wall. In Paul-Hausen solution, we have an isothermal wall. So there we define theta in such a way that it will become zero at the wall, but here we do not have such a kind of thing. So we'll have to define slightly differently. So I'll define theta as T infinity divided by, because this is an adiabatic wall, I do not know the wall temperature. I cannot use any reference temperature with respect to wall. So I'll have to use a different metric. So I'll be using U infinity square by 2Cp, and this also has the same units as temperature. So this will be the non-dimensional variable that I'll be using. And with this non-dimensional variable, we are saying that this is only a function of eta. We will use the same similarity variable as before, which is eta is this is same as the one that we got in the Blazer solution. I'll just use added a two-factor here, but that's fine. Now, can you do the similarity transformation? You will also need u and v. Maybe I'll give you those values directly so you can do the transformation yourself. I'll wait for, let's say, 5 to 10 minutes. This might take a little more time, so you can try solving it yourself. From the Blazer solution, we have u as u infinity times f prime of eta. And then you also need to know v value. So v is given by, how do I get v? You can actually take the continuity equation, do the integration, and from there you can actually get the v value. Anyways, I'll give you the value directly, so you don't have to do that again. So that comes as half into square root of mu u infinity by x times eta f prime minus f. This is the value of v. Yeah, now we can use these. With this, I think you will be able to do. First, you have to do the non-dimensionalization of this equation, and then you'll have to take the derivatives, substitute them back into this equation, and eventually come up with your governing equations. That might take some time, so take like 5-10 minutes and you can solve it. And we also need to know the boundary conditions for this particular set of equations. So for an adiabatic wall, I have del t del y at y equal to 0 should be 0, which will translate to del theta, sorry, just write theta prime of 0 equals to 0. And then what will be my other equation? Yeah, at free stream, this should be equal to 1. So previously, when we were solving the Paul-Hausen equation, our boundary conditions were, this is in the current case. In Paul-Hausen case, we have theta at 0 should be equal to 0 and theta of 1 equals to, sorry, at infinite theta equals to 1. But we do not know what theta prime of 0 is. This is Paul-Hausen case. In the present case, our problem is we do not know theta of 0. So you see the problem. So if you want to, if you try to convert this into an initial value problem, in the Paul-Hausen case, we would have a problem because we do not know theta prime of 0. So we'll still have to do that shooting method where you make a guess and then try to integrate till infinity, get the theta if infinity, which will not be equal to 1, and then you'll have to update your guess in such a way that theta of infinity becomes 1. That is what we were doing. That is called shooting method. Now, for the current case, what is happening is I know theta prime of 0, but I do not know theta of 0. So now I will have to make a guess of theta of 0. And with this guess, I'll have to calculate theta of infinity, and again do the same thing as before. So the same kind of code will actually work in both the scenarios, just that previously heat flux is not known at the boundary. Now temperature is not known at the boundary at the wall. That's the only difference. But still, this requires the iteration loop that I was discussing before. Maybe I can explain that also a little while, or yeah, I'll leave that part. You can actually solve the same equation using the IVP problem I discussed, or you can use the solve BVP, the solve boundary value problem, the solve BVP function in Cypher to solve this. Yeah, but solving is a different thing. First, you can derive the governing equation first, and then we will see how to solve that later. If you're interested, you can I can actually share the Python code for that also. Do let me know in the comments, or you can fill in the feedback form. I'll share later. Yeah, you can start with deriving the equation. I'll wait for let's say 5 minutes. Yeah, I guess you are kind of halfway through the derivation. So I'll start writing the equation so you can compare if you are getting the same answer. So let's start them term by term. First step is non-dimensionalizing the equation. So our governing equation is rho Cp, sorry, del T del x. is V times del t del y is K times del square T del y square, the conduction term and the viscous dissipation term, which is del u del y whole square. First step is non-dimensionalization. Theta is already given to us, so T is given by T infinite, the free stream temperature, plus the excess temperature that you are getting because of viscous dissipation, U infinity square by Cp times theta of eta. So now from this I can calculate, and we already know eta is given by y times square root of u infinity by mu x. So del t del x is given by half u infinity square by Cp times theta prime times del eta del x is eta x, is basically minus eta by 2x. Basically 1 by square root of x is 1 by 2 times square root of x, so that will be eta by 2x. And similarly del t by del y is half u infinity square by Cp times theta prime times del eta by del y, which is square root of u infinity by mu x. So now I can substitute my original equation to this. So I'll have u times del t del x, the advection terms, plus v times del t del y. U is u infinity times f prime times half u infinity square by Cp theta prime minus theta by 2x, plus v is given by half into square root of mu infinity by x times eta f prime minus f times del t del y, which is half u infinity square by Cp theta prime square root of u infinity by mu x. If you simplify this, that will come out to be u infinity cube by 2 Cp times minus half f theta prime, and then we have an x. These are the advection terms. Now we have to consider diffusion and the viscous dissipation terms. So the diffusion term is del square T del y square. So this is the same equation. We will have to do the derivative with respect to y again. That will give me u infinity square by 2 Cp times theta double prime into eta by d eta by dy is again the same term. So that will be u infinity by mu x. So this is coming to be u infinity cube by 2 Cp into theta double prime. This looks like mu. This is theta double prime by mu x. So this is the conduction term. Now we also need to calculate the dissipation term. So I know del u del y is u infinity times f double prime into eta y, which is square root of t by mu x. So we have all the individual terms that we need. So we'll have to just substitute them, like put them together in our original equation, which is this equation. So which gives me rho Cp times the advection term, which is u infinity cube by 2 Cp into minus half f theta prime by x equals the conduction term, which is k times u infinity cube by 2 Cp theta double prime by mu x plus the diffusion term, which is mu times the square of this term, which is u infinity square u infinity cube by mu x into f double prime square. Now we'll have to do a little rearrangement. I can cancel u infinity cube by 2 Cp, and then I can rearrange these equations a little. So x will get cancelled throughout. This is another thing. So we assume x is not equal to 0. So at the leading edge, we have a singularity. This is another point I would like to stress. I think I kind of missed this somewhere before. Is whenever we define eta, eta is our similarity variable, which is defined as y times square root of u infinity by nu x. So the way we define this eta is such that when x equal to 0, that is exactly at the leading edge. So this is my leading edge, this is how the profile looks. So this is my x equal to 0. At the leading edge, we have eta tends to infinite. So we have a singularity at the leading edge. So this particular solution that we are deriving from the similarity, whatever Glacier solution or the Paul-Hazen solution, or even the one that I'm deriving currently, all of them use the same similarity variable, which is not valid exactly at the leading edge. So what does that mean physically? Physically, when you see the equation, the boundary layer equations that we got are parabolic in nature. So which means they can be marched forward in x direction, parabolic with respect to x. Along the y direction, you have the diffusion term, so they become elliptic, but along the x direction, it is parabolic. However, at the leading edge, where eta is not defined, we cannot actually use a parabolic form of equation. So there are different techniques for that. One would be you do not even consider the boundary layer equations, take the full elliptic equation. The Navier-Stokes equations are themselves elliptic in nature for incompressible flows. So you'll have to solve the full elliptic equations, especially near the leading edge. In this region, you'll have to solve the elliptic equation. The parabolic equations are valid only when you are certain distance apart from this. But the interesting point is, even though the actual solution is not valid here, the terms like the average Nusselt number or the average skin friction coefficient are not impacted significantly under the laminar region because of the singularity that you are going to get here. So if you are interested in that, you can actually explore. There are several papers on what happens near the singularity and how to deal with singularity, etc., etc. If you're interested, you can look up on them. Again, which is not part of this course. As far as this course, what we are concerned is the effect of this leading edge is kind of not important when you are sufficiently far from Earth, and when you are using calculating the drag force or the total heat transfer, you would be using only the averaged quantities, which essentially integrate across the thing. And when once you do that integration, the effect of the singularity kinds of vanishes. Like the error terms become very negligible, so that we are actually neglecting this will not actually affect significantly on your final results of our interest, like the total drag force or the net heat transfer, the average heat transfer. So this is just a subtle point that I would like to just highlight here because it came up here again. Now that x and these terms are cancelled, so we'll have minus half times f theta prime. So we will have a k times rho Cp. So this will be k by mu Cp times theta double prime. And then we have rho times mu is mu, mu by mu is 1. So we have f double prime square. So this equation, I can rearrange this as k by mu Cp is 1 by Prandtl number. So theta double prime plus Prandtl number by 2 times f theta prime, and then we have Prandtl number times f double prime square equal to 0. And our boundary conditions are, at the wall it is adiabatic, so theta prime of 0 is 0, and at the free stream it should be equal to 1. So this is a set of equations for uh, when you have non-negligible viscous dissipation with adiabatic wall. If you compare this with the Paul-Hazen term, Paul-Hazen solution, Paul-Hazen equations, we do not have this extra term in the Paul-Hazen equation. So we would just have theta double prime plus Prandtl number by 2 times f times theta prime. Only these terms are there in the Paul-Hazen one. This is extra term that is coming because of viscous forces. So you can also simply understand this as f double prime is something that is relates with shear stress. As you know that f double prime of 0 is a shear stress of the ball. So this f double prime is something that is related with the shear stress. So as the shear stress increases, this particular source term increases. This is just to kind of understand, just to understand this little more. Yeah. Now you can solve this, like we already know f value, so you can solve this and plot for different values of Prandtl number and etc, 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 which we are not doing currently because for that you'll have to actually use, like we cannot directly solve this analytically. We'll have to use some numerical technique because f itself is not. Otherwise, you can use tabulated values of f and then solve an analytical solution for this. That is actually straightforward and you can do that, which I'm leaving again as an exercise. Are there any questions? Yeah. Okay. Now, to summarize what we have been discussing till now, we started from we discussed about Blasius and Paul-Hazen equations, which are essentially exact techniques to solve similarity solutions. So we started with the boundary layer equation in the last week, and then from there in the lecture videos, the derivation of these have been discussed in detail, where we came up with certain equations and the boundary conditions, where we have only one variable we introduced the concept of similarity variable. So the original problem, which is a function of x comma y, reduced it to a single variable eta, which is given by this expression. And then we got the differential equations, and subsequently we solved different problems where the important concepts like the Reynolds-Colborn analogy is discussed, where you can, if you know the skin friction, from there you can calculate the average heat transfer coefficient. So that is given by h bar by rho cpu infinite is given by skin friction coefficient by 2 times Prandtl number to the power 2 by 3. Of course, this you can neglect. For in Reynolds analogy, you do not have this one. So the idea here is, if you know the drag force, you can calculate the skin friction coefficient, and from there you can use this relation to calculate the heat transfer coefficient. So this is one analogy that we have, and this comes essentially from the fact that your boundary layer equations for velocity and temperature look similar. Again, for Prandtl number equal to 1, they will be more or less the same. They'll actually be the same if your boundary conditions are also isothermal, which is again discussed in detail in the lecture videos. So I would advise you to go through the lecture videos to understand the similarity or the analogy much better. And then we solve some problems of where you will be asked to find the boundary layer thickness or the surface shear stress or the drag force or the heat transfer. We have solved all the variants that are possible, but we have only considered the cases where the wall temperature is assumed to be isothermal. Only the last problem is where you have an adiabatic wall. There are other problems also where we discussed that the concept of film temperature is actually important, where we discussed that in order to calculate this Nusselt number, etc., you will require to know the thermophysical properties, and all these thermophysical properties should be evaluated at the film temperature. So in this week, I have only considered the cases of isothermal wall. So calculation of this film temperature is straightforward. But we will also consider in the next week a problem where the temperature is not known. So for example, when you have an isoflux boundary condition, basically constant heat flux boundary condition, then you will not know the temperature of the surface. Then you cannot calculate the film temperature. Then what temperature should you use to calculate your fluid properties? There we'll have to use an iterative solver. So you'll have to assume a temperature, calculate the film temperature, calculate all the properties, calculate from there, calculate whatever is of your interest, and somehow need to assess whether the calculations are correct or not, and then update your film temperature. And you have to keep doing this till the final value does not change much. We will see this in detail in next week. I'll take up a problem with the constant heat flux case also, then it will be much more better. But for now, for simplicity, we have only solved an isothermal case where the concept of film temperature is introduced. And subsequently, we understood that uh, the reduction in drag or and the heat transfer, these are kind of related. This is some kind of optimization that we discussed in the last week also, where we observed that if you try to increase heat transfer coefficient, you will have to reduce the thermal boundary layer thickness. But because thermal boundary layer thickness and the velocity boundary layer thickness are related with each other, reducing the thermal boundary layer thickness will also reduce the velocity boundary layer thickness. And if velocity boundary layer thickness reduces, the shear stress will increase. So if you try to increase heat transfer, your shear stress will also increase. So you will have to pay price for increasing the heat transfer. So this problem is one such problem where you understand that in order to get net savings, you have certain criteria that needs to be satisfied, and you use the existing correlations to identify those criteria. And then we discuss one more problem that extends the Colburn's analogy that I just spoke about. And then we understood how to solve the Blazes equation by treating it, by assuming that the prerequisite for this is you know the how to solve an initial value problem already. Then the typical way to go ahead is use a nonlinear solver that can solve this kind of system. But then we've used a different technique where instead of using a nonlinear solver, we use only we integrate it only once. But then we use the property that the basis equations are invariant to scaling. And with that property, we actually evaluate the value of, we actually solve this equation with only in one step, in a single step. This is kind of valid only for this pattern. So it's the general idea is to know the general technique where I kind of introduced you to a boundary value problem that is already available in the SciPy module of Python that you can learn yourself. If you have any questions, please write to me. I can share the code of that as well, and we can discuss in next week. And next problem we discussed is when even though the boundary layer equations are derived purely for external flows, there can be scenarios where the flow looks like internal, but there can be certain regions within that where you can extend the ideas that are discussed in the boundary layer. So, and what the criteria are, etc., is something that this problem highlights. And then we discussed about the transition to turbulent, all the boundary layer equations that we derived. You need to be careful about the assumptions that are taken, like the incompressible flow, the pressure variation across, there is no adverse pressure gradient for the flow. And then comes the transistor, the flow is lambda. So for each of these, you need to know what are the criteria that can help you to establish these assumptions. Like for the incompressibility, you need Mach number less than zero point 0.3. For the transition turbulent, you need to know the local Reynolds number less than 5 to 10 power 5. And for the adverse pressure gradient is something that I have not introduced yet, which is something that we will discuss a little later into the course. So knowing these assumptions and how to verify them is important before you solve the problems and which correlations to pick. It will also help you to decide which correlations to pick for your particular problem. And the final one is where the effect of viscosity is also considered. This is just to highlight and kind of an exercise problem where you can try to develop your own similarity solutions. So you assume it's a certain kind of similarity and then use the same kind of transformation and finally get the equation. Now you do not have to do all of this with hand. Now we have several symbolic tools, like if you're familiar with Mathematica or the SymPy library in Python, or if you're familiar with Julia language, there is symbolic toolkit. There are different toolkits that are already available, so you do not have to do this manually now. So you can just give the relations and they'll actually do the solving for you. Like they'll actually do the solving, like you do not need the equations. They'll give you the final solution also. So we have advanced tools right now. And we also discussed about an important singularity that we are going to get near the leading edge in Blaze's kind of solutions. And the reason that it is a singularity is because of twofold thing. One, at x equal to 0, we do not have this. And the other main important point is the governing equations that we are considering are parabolic along the x direction, which is not valid, especially near the leading edge. However, the effect of that on the cumulative quantities like the net drag force or the net heat transfer is not that significant. So we can still use the correlations that we developed by ignoring the singularity. Of course, if you are very close to the wall, then you will have significant deviations, which is again something that if you are interested, you can look up papers on that. Yeah. If you do have any feedback on the sessions, please do fill them. I'll try to incorporate those things from next session onwards. I'll wait for a couple of minutes, or yeah, if you do have any questions, you can type in the chat box or you can unmute yourself. If you do not have any questions, I think this is all from my end. Thank you for joining, and we'll meet the same time next week from uh, 5 to 7 next Saturday. Thank you all for joining.